today we will look at the concept of poles and relative poles and see how we can use that for the synthesis of function generation mechanisms. Okay. So, we saw earlier, so if you look at two positions of the coupler A1 B1 and A2 B2, right. So, if I have a 4 bar, then if I look at, so this is the perpendicular bisector of A1 A2, B12 is the perpendicular bisector of B1 B2, and we saw that the two perpendicular bisectors intersect at a point which we call the pole. Okay. And what the pole essentially tells us is that I can move, pole is the point on the coupler that does not change when you move it from, when you move the coupler from position 1 to position 2, or in other words A1 B1 will move to A2 B2 about a pure rotation, with a pure rotation about P12. Okay. So, this pole P12 depends only on the initial and final positions, it is independent of what happens in between. Okay. So, the pole is pole P12 depends only on the initial and final positions and is independent of the actual movement of the coupler. Of the coupler. So, now if the pole means that, okay, I can move from A1 B1 to A2 B2 by a pure rotation, then so I have, when A1 B1 moves to A2 B2, the rigid body is rotating about an angle theta 1 2. Okay. So, if I take any line on this rigid body and move it to the new position and this line. Okay. So, essentially P1 to A1 is a line on the rigid body, B1 A1 P12, right, if I look at that. So, then this has moved through an angle, it has rotated about the pole by an angle theta 1 to 2, theta 1 2. Okay. So, then if I look at this angle, which is the angle to the perpendicular bisector, right. So, that angle is half of the total angle that the rigid body rotates by. Okay. So, A1 B1 also I can say has rotated by the same angle, any point on the, any line on that rigid body would have rotated by that same angle when it goes from position 1 to position 2. So, this is theta 1 2 by 2. So, here you have, so if I look at these two triangles, I have A1 P12 A2, that angle is the same as the angle that B1 P12 B2 makes, and this is theta 1 2. And therefore, this angle or this angle B1 P12 to the perpendicular bisector, the angle which it makes with the perpendicular bisector is theta 1 2 by 2. Okay. So, now if I look at the frame, okay, frame OA OB, angle subtended by it at the pole. is OA, this angle OA P1 to OB, that is the angle I want to look at. Okay. So, if I do that, I have, this is what I am looking at, angle subtended by the frame at the pole. Here I have this angle is theta 1 2 by 2, okay. And then I have this part of the angle, okay. I have this angle that I want to determine, or so it is this angle plus theta 1 2 by 2 is the angle subtended by the frame at the pole. Similarly, if I look at angle subtended by the coupler, A1 B1 at the pole, that angle is A1 P1 to B1, okay, which is A1 P1 to B1. So, again here I have this angle is theta 1 2 by 2, and then I also have this angle which is the same as the previous angle, the red and the orange, those two angles that are the same. So, I am adding theta 1 2 by 2 to both of them. So, this means OA P1 to OB equals A1 P1 to B1. Okay, you have to make sure that you follow the same order. If this is OA, this should be A1. You are measuring from this line to that, same order. Okay. OA P1 to OB, this should not be B1 P1 to A1. Okay, then the sign will change. Follow the same order. So, these two angles are the same. So, essentially the angle subtended by the frame at the pole is equal to the angle subtended by the coupler at the pole, and this is a fact that is quite useful for dimensional synthesis that we will use to. Similarly, if you look at the angle subtended by the crank, similarly angle subtended by crank, which is A1 P1 to OA equal to angle subtended by the follower. Angle B1 P1 to OB. Okay. So, be careful in measuring the angle. You have to, if this is A, this should be A, okay, not the other way around. So, you will see that in the next one when they sometimes, so it would either be equal or will differ by 180, as you will see in the next one. So, this is the property we will use when we do the synthesis. So, if you see here, if you measure the angle subtended by the frame at the pole, how would you measure it? If you take it as OA P1 to, this is OB, then OA P1 to OB would be this angle here, okay, and you compare with A1 P1 to B1, A1 P1 to B1. So, this is A1 to P1 to B1, which is this angle. Okay. So, you can see that these two angles differ by 180. Okay. So, this equals this plus 180. Okay. So, when the poles on the, when the pivot is on the other side of the pole, you will find that they differ by 180. When they are on the same side, they are equal, okay, in this case. So, now because this angle is equal to this angle, theta 1 2 by 2. So, this is what we will use for the dimensional synthesis, and we can also define a relative pole which would be between the two moving links, which are the crank and the follower. So, between the coupler and the frame, that point is the pole. To relate the motion of the crank and the follower, we call that point the relative pole. We define a point similar to that called the relative pole. Okay. So, let us look at the definition of the relative pole. So, here you have a function generation, a linkage where the crank rotation of phi 1 2 results in a follower rotation of psi 1 2. Okay. This is your, these are the linkage displacements that need correlation. So, you need to design a function generation linkage for to accomplish this goal. You have a question, the previous one? They are different. The pole relates the coupler with the fixed link. The relative pole relates the crank and the follower. So, in the 4 bar you have the 4 links, right. Coupler with respect to the fixed link is what we call the pole. Relative pole is relates the crank with the follower. So, let me just, pole is used to define a finite movement of the coupler with respect to the frame. Same concept extended to study the relative motion between the crank and the follower of the 4 bar. So, let us first look at, again to understand this, we look at inversion. Okay. So, this is the 4 bar linkage you want, which correlates a crank displacement of phi 1 2 with a follower displacement of psi 1 2. Now, instead I make the crank the fixed link. Okay. So, I sit on the crank, OA A1 becomes my fixed link. And what did we do? We looked at, so if you look here now, by inversion, once I sit here, this OA OB B1, okay, first rotates by minus phi 1 2 Okay. I rotate by the angle minus phi 1 2 to bring the frame close in the second position, and then so this is OB dash, and initially B1, if I move this as a rigid body, it goes to B1 dash, but B1 dash should actually OB B1 dash should actually have moved a psi 1 2 in the second position. So, this becomes my B2 dash. This is what we did last class with the inversion. Okay. So, B1 moves to B2 dash, right, and if you look at this thing, now this is my fixed link, I can look at the displacement of the follower as moving from OB B1 to OB dash B2 dash. Inversion again, I am just, so this now becomes the coupler essentially for this link. I have moved from OB B1 to OB dash B1 dash. So, if I find the perpendicular bisector, so OB has moved to OB dash, again we want to find the point about which this motion has happened as a pure rotation, right. So, OB dash perpendicular bisector, which is this one, then B1 B2 dash perpendicular bisector, this one. Where they intersect, this point I call it the relative pole, because it's basically the pole for this linkage when the crank is the fixed link. The only reason we call it the relative pole is in my original linkage it is not the fixed link. Okay. So, it is the same concept. OB B1 moves to OB. So, these two rotations can be combined to a single rotation about this relative pole. The two rotations, which are the two rotations? Minus phi 1 2, this one, and psi 1 2, this one. So, if I look at OB B1, first it is moved by minus phi 1 2 and then by psi 1 2. Okay, think about it initially as welded like that. I move that by minus phi 1 2 and then I remove that weld and then move that alone. OB B1, move it relative to OA OB dash by psi 1 2. So, if I look at the net rotation of this body OB B1, it is in the plane, it is minus phi 1 2 plus psi 1 2. So, that is my theta 1 2 for OB B1. OB B1 has rotated by this angle. Yes, rotated by this to OB dash B2 dash. Initial position, final position, about this point the total rotation is minus phi 1 2 plus psi 1 2. So, that is the relative pole is the point about which this rotation is happening, this net rotation. Okay. So, relative pole is the point about which these two rotations minus phi 1 2 comma psi 1 2 can be combined into a single equivalent rotation. So, in the planar case it is very easy, you are just adding them algebraically, the two rotations for this rigid body. Okay. So, now let us see how we can use this for synthesis. We will develop some relations between these various angles and then use that to for synthesis. Okay. Okay. So, let me call this angle alpha here, the angle which, so I have the relative pole OB to the relative pole, the line from OB to the relative pole, let us say it makes an angle alpha. Okay. This I know is minus phi 1 2, this angle here is minus phi 1 2, and OB B dash, this line here C dash 1 2 is the perpendicular bisector of which line? OB OB dash, probably not right. Okay. So, this angle here is going to be half of minus phi 1 2, this angle is that. Now, beta, okay, if I look at the rotation of OB B1 to OB dash B2 dash, so I may, this is the half the rotation from the first position to the second position. So, if I said if you have theta 1 2, which is the rotation of OB B1 to OB dash B2, okay, because R12 OB would have rotated to R12 OB dash by a certain angle, and half of that angle is beta in this direction. I am moving from position 1 to position 2. Yes? Okay. So, now if I look at this triangle, in triangle OA R12 OB, alpha is an external angle. Okay. So, I can write alpha equal to minus phi 1 2 by 2 minus beta, because I have taken beta in this direction, which is from position 1 to position 2, okay, because I take beta as the angle of rotation from position 1 to position 2, it is opposite, it is measured opposite to the direction of minus phi 1 2, so it is minus beta. Okay. So, beta is taken as negative, because it is measured opposite in direction to phi 1 2, sorry, minus phi 1 2 by 2. Okay. So, that means alpha is this. Now, I already showed you that the rotation beta is essentially half the angle that any line on this has rotated by, when this is the coupler. OB B1 rotates to OB dash B2 dash, half, which is we saw in the previous slide, that angle is psi 1 2 minus phi 1 2. That was the angle that OB B1 rotates to OB dash B2 dash. Therefore, beta is half of this angle. Okay. Because the net rotation of OBB1 to get to OB dash B2 dash is psi 12 minus phi 12, minus phi 12 plus psi 12 as I showed you. So, this is beta is the angle with that perpendicular bisector. So, it is half that angle. Okay. So, now if I substitute, I get alpha equal to minus phi 12 by 2 minus psi 12 by 2 plus phi 12 by 2 equal to minus psi 12 by 2. So, if phi 12 is clockwise, minus phi 12 will be counterclockwise. If psi 12 is counterclockwise, minus psi 12 would be clockwise. So, you would take the direction based on what the original required rotations are. Okay. So, if you look at the relative pole now, what is the relative pole? If I have the frame OA, OB, I can directly find the relative pole knowing my design criteria phi 12 and psi 12, because alpha I have found is nothing but minus psi 12 by 2. So, I can draw a line from OB at minus psi 12 by 2. I can draw a line from OA at an angle of minus phi 12 by 2, and where those two lines intersect gives me the location of the relative pole. Okay. Let us do a synthesis, then it will be clear. One more thing, if you look here, because this is just the same as the initial case with the pole where you looked at the coupler and the fixed link, right. So, now what do you know? This, the angle that OBB1 makes at the pole, okay, or sorry, the angle that OA-OB makes at the pole again is going to be the same as the angle that A1-B1 makes at the pole, at the relative pole. We saw earlier, because that becomes the crank and the follower for this mechanism. We saw earlier with the poles that the crank and the follower also make so, if you see here at the pole, this angle made by the crank is the same as the angle made by the follower. Okay. So, what we will use is the fact that OA, OB makes a certain angle at the relative pole, and that is going to be the same angle made by the coupler A1-B1 at that relative pole. Okay. So, viewed from R12, OA-A1 and OB-B1 subtend equal angles. Also, it is the same with the frame and the coupler OA, OB and A1 B1 also subtend equal angles at R12. Therefore, we will use angle A1 R12 B1 equal to angle OA R12 OB. So, now if I know OA OB and I know phi 12 and psi 12, I can find the relative pole. Okay. I can assume some A1 for the crank length, same as what we did for inversion. Okay. I need one and I need to find B1. And how can I find B1? If I know this angle, once I find the relative pole, I know the angle subtended by OA OB at that point. B1 should be such that A1 B1 subtends that same angle at that relative pole. Okay. So, that is how we will use it for the synthesis. So, I am given OA, OB, okay, and I know this alpha is, so I want to find the relative pole. I want to coordinate these two motions. Motion of phi 12 on the crank should result in a motion of psi 12 of the follower. Okay. So, to do that, I have my OA OB picked out. So, I draw a line from OA at an angle. What will this angle be? If this is clockwise, so this is the angle minus phi 12 by 2. Okay. Then from this point OB, I draw a line at an angle to the frame of minus psi 12 by 2, where those 2 points intersect is my relative pole 1 2. Okay. So, now I pick some point, so some crank length A1. So, I pick A1 is a choice I make. I have not used it so far, I only worked with the frame, right. I found this angle. So, this is the angle subtended, let us call this angle beta, the angle subtended by the frame which is OA OB at the relative pole, that is my beta. If I measure from OA R12, see I know A, that is why I am measuring it in this direction now, because now I have to, from A I connect A to, this does not look different, so let me go with, from A I connect to R12. Okay. I know that the angle that A1 B1 will subtend at the relative pole should be the same beta, same direction when I measure from A, okay, from A to B should. So, this line I construct at an angle beta. If I pick any point on this line, my A1 B1 will subtend the same angle at the relative pole. So, I have an infinity of choices for B1. I can pick B1 any place on this line to complete my linkage. So, that is how I design my follower length and my coupler length. Now, this linkage, if I move the crank by phi 1, the follower will move by psi 1. Okay. Any questions? A1 was also a free choice, or it may have been specified because of other considerations. But essentially I have A1, I have infinity square choices, could be anywhere on the plane. Then B1 I have how many choices? I have an infinity of choices, because it has to be somewhere on this line u, which is at an angle beta to the line joining A1 R2. Any questions? So, this is the way you would use the relative pole to design a function generation mechanism. You can do the same thing. This is a 2 position function generation. That is the solution. I can use it for 3 position function generation. I have here the crank has to move phi 1 2 and then 2 to 3, phi 2 3. So, I can get phi 1 3. So, phi 1 2 is essentially phi 2 minus phi 1, right. That is the definition, 1 from 1 to 2. Okay. Similarly, psi 1 2, psi 2 3, I have this. So, if I pick my OA, OB, what do I do first? I locate which relative pole? I can locate R 1 2. So, what would this angle be? Minus phi 1 2 by 2, then from OB okay. So, that gives me relative pole 1 2. Okay. So, I measure this angle. Beta from 1 to 2. So, let us call that. Then I choose A1, I connect A1 to R12, measure of that same angle beta 2 in this direction, same angle, and this line so my B should lie somewhere on this line. But now because I have an additional condition, I cannot pick B anywhere on this line. It has to also satisfy the conditions for position 1 and 3. Okay. So, to do that, I construct the second relative pole, which is at an angle minus phi 1 3 by 2, this line, intersection of that, and what should this angle be? Minus psi 1 3 by 2. So, this gives me R 1 3. And if I look at what is the angle made by OA R 1 3 with R 1 3 OB, then I get this angle is beta 3. So, I join A1 R13, take the same angle beta 3 to construct another line which will intersect the first line at the point. What point is this? It is B1. Okay. So, this is using relative poles instead of inversion, using relative poles to construct a function generation mechanism.